Hi, my name is Ashika Thuria, and this is my Physics 2212 Lab 3 report analyzing the magnetic field of a bar magnet. As an overview of this presentation, I'll go over an introduction of the experiment and presentation, including the purpose and main results, as well as important concepts and formulas necessary in this lab. I'll then go over the experiment and calculations, a computational model, its input code and results, and I'll finish up this presentation with some follow-up questions. The purpose of this lab is to explore the correlation between the magnetic field and observation distance on and off axis. Here are some main results which we'll further discuss later on in the presentation. Firstly, we'll discuss the concept of the magnetic field of a dipole and how that's similar to that of a bar magnet. Bar magnets' magnetic field occurs in the same pattern as that of a dipole, running from the positive charge outwardly to the negative charge. Lastly, we'll discuss the idea of superposition. The principle of superposition states that every charge in space creates a magnetic field at a point independent of the presence of other charges in that medium, and that the resultant magnetic field is a vector sum of the magnetic field due to the individual charges. The top two formulas describe the magnitude of the magnetic field due to a magnetic dipole. This will be helpful later on when we solve for the mu value, the magnetic dipole moment of that magnet. The next formula will allow us to linearize our experimental data, and the bottommost formula describes the magnetic field of a dipole at any location. At the bottom of this slide, a diagram of the setup of this experiment is shown. In this experiment, we have defined the system as the observation point and the surroundings as the bar magnet. With this information, we will first determine the direction of magnetic north and then set up the meter stick in the position orthogonal or perpendicular to that northern direction. Then we'll locate the magnetometer of the phone and move the phone along the meter stick and record data from these positions. Here's a spreadsheet with the experimental data as well as a graph that depicts the natural log of bx by the natural log of r. At the bottom of the spreadsheet, you can see the net magnetic field at the location 45 degrees off axis from the dipole. I'll use this data in further calculations. Here are the main calculations of the experiment using the data from the previous slide. Here, I was able to set the two equations on the left equal to each other so we could solve for the mu value, and then use the slope value from the experimental data from the previous slide to solve for n using the formula previously mentioned. I was also able to solve for the k value using the y-intercept of the y equals mx plus b equation from the experimental data. Using that data, I was able to plug those values into the equation for mu and solve for that value. Mu ended up coming out to equal 2.375 Newton meters per Tesla. For this lab, I used the GlowScript starter code to generate a computational model to represent this data. In this code, I inputted the magnitude of mu, which I just solved for in the previous calculation slide. I then wrote a function to describe the magnetic field due to a dipole with a given magnetic dipole moment and a specified observation point. Then set the location of 6 different positions to visualize, 2 of which are on the dipole axis and the others are perpendicular to the axis. I then associated arrows for each of those observation positions, as well as one to represent magnetic field 45 degrees from the axis. These are the results generated from the code. The orange arrows represent the 2 on-axis magnetic fields, and the blue arrows represent the perpendicular magnetic fields. The small pink arrow in the top right corner is the magnetic field at the 45-degree off-axis observation location. In this diagram, the scale magnitudes of the magnetic field at various observation locations are evident. From this 45-degree vector, we are able to find the magnitude and compare it with our measured data. The average B net from the experimental data is 5.529 E negative 5. After calculating the magnitude of B net from the vector given in the code, we can conclude that the magnitude is 1.4336 E negative 5. As you can see, these values are very similar and probably vary due to human error in measurement. To conclude this presentation, I'll answer the following questions about the observations. The only observations of these 4 that hold true are that the magnetometer measures a near zero magnetic field in the x direction when it's far away from the magnet, and that as the distance between the magnetometer and the magnet gets smaller, the measured x component of the magnetic field increases. If we hadn't oriented the experiment to take into consideration magnetic north and just laid out the meter stick at any angle, all values for Bx would have turned out to be off by the angle away from the north, but because all of these values would have changed, the difference between values would not be any different. If I stuck two magnets together end to end, I'd expect each measurement to be multiplied by a constant, yielding only a different magnetic dipole moment. Thank you very much.